Alright, section 10.2. Again, I'm going to put this in about 10-minute sections. I'm not sure how many sections that's going to be for 10.2. Okay, in section 10.2 they get around to talking about tree diagrams. We've already been drawing a lot of tree diagrams, so we really don't need to discuss the tree diagrams too much. Draw one branch for each outcome, place a label at the end of the branch, and we've been doing that over and over again. So in this case we have a tree diagram for drawing a red, white, or blue ball. So if you have a one-stage tree diagram, that just means that you have done one thing. You have drawn one ball, you have flipped a coin, you have rolled a die, and then it gives you the outcomes for that first action. Then at the end of each one of those branches you can have another set of branches, and those are called secondary branches, and those tell you what has happened with your second procedure or second outcome. So here we have a red, green, yellow, and white marble, and we're going to choose one without replacement and choose a second. So we have the sample space somewhere else in your notes, but the first stage are red, green, yellow, and white, and the second stage are the ones that are at the ends of each of the first stages. And there are 12 possible outcomes there. So how many outcomes in the tree diagram correspond to getting either a red or a green marble first and either a yellow or a green marble second? So we're going to start with red or green marble first. Let me change my color. So red or green marble first, meaning I don't need to look at this part of the tree. And we're either going to get a yellow or a green marble second. Green, yellow, not interested in the white, not interested in the red, not interested in the white. So that is 3 different outcomes. Red, green, red, yellow, and green, yellow. The fundamental counting principle, again, this is something that we used in a previous chapter. And essentially what the fundamental counting principle says is we can take the number of ways that a particular event can occur, and we can multiply it times the number of ways that another event could occur, and that tells you how many events we have in all. I think the example we used before was a man goes on a trip and he packs pants, shirts, and ties, and an outfit is made up of pants, shirts, and ties. So how many different outfits could he have? So here's another example. It's a pizza example. So the options are you could get a small, medium, or large, you could get white or wheat crust, and you could get sausage, pepperoni, bacon, onion, or mushroom. How many different one-topping pizzas are possible? So for the first one, what you're going to do is you're going to choose the size. You have 3 sizes to choose from. Then the second thing you're going to do is you're going to choose a crust. And you have 2 different crusts to choose from. We could get white or wheat. Then you're going to choose what topping you want. There's 1, 2, 3, 4, 5 toppings. Counting principle says all we have to do is multiply those together, and there are 30 different possible pizzas. So in the previous example, what is the probability someone randomly selecting a large whole wheat pizza with any of the 5 toppings? Well, we know that there are 30 pizzas. That's the number of items in our sample space. So we need to find out how many large whole wheat one-topping pizzas there are. Well, there's only one way to choose a large. There's only one way to choose whole wheat, and you have 5 toppings to choose from. So multiply those together, 5 different pizzas. So your probability would be 5 over 30. Find the probability of getting a sum of 11 when tossing a pair of fair dice. Well, again, the first die you have 6 possibilities. The second die you have 6 possibilities. 6 times 6 is 36. And again, you can count those. They're in your book. Now the way to get a sum of 11. Sum of 11 is 5 and 6 or 6 and 5. So there are 2 ways. So the probability is 2 over 36. Again, I won't put any card questions on the test, but suppose 2 cards were drawn from a standard deck. Use the 2-stage tree diagram to find the probability of getting a pair. Now this is only part of the tree. This tree is huge. So there are 52 primary branches because there are 52 cards in the deck. Primary branches being the branches in the first stage. And this is your first stage. Then there are 51 secondary branches that come out from each one of the 52 branches that we had initially. So if we use the counting principle, 52 times 51, there are 2,652 possible outcomes when you pull 2 cards out of a deck. So if we think about what results in a pair. A pair, you can have any one of the 52 cards. So with the ace, you have 3 other aces. With the king, 3 other kings, so on and so forth. So that's 52 here. 3, because each one of these is 3, so 52 times 3, 156 pairs. So that means that the probability of drawing a pair is 156 over 2,652. Or if you simplify that, it's 1 over 17. Okay, this would be a good place to pause and start a new recording.